This is going to be a short video proving that the harmonic series diverges. So the harmonic series is an infinite series built out of 1 over k, starting with k going off to infinity. So when you start to expand this sum, it looks like 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, etc., etc. Maybe it seems like it's going to converge. It actually does not. Typically, when people prove that the harmonic series does not converge, they show that it blows up to infinity. I'm going to take a different route, kind of sticking with recent themes in Real Analysis 1. I'm going to prove that the sequence of partial sums is not Cauchy and therefore not convergent. It might be less informative than showing how the partial sums kind of blow up to infinity, but I actually like this proof better than the traditional proof. Okay, so I'm going to prove it's not Cauchy. So what I'm actually going to do is fix a choice of epsilon. Let epsilon be a quarter, and then choose any capital N from the set of natural numbers. The idea is, for this choice of epsilon, propose this as a threshold. I'm going to show that it won't work as a threshold in the definition of a Cauchy sequence. Namely, I can find two partial sums beyond this candidate threshold whose pairwise distance to each other is greater than epsilon. So to do that, choose little n from the set of natural numbers so that 2 to the n is greater than or equal to capital N. In fact, you could just pick 2 to the capital N, but let's just do this. Okay. So for this choice of epsilon, I'm proposing this as a threshold, and then I'm going to say, hey, here's a term beyond the threshold. I'll pick another one in just a second. Let's look at their pairwise distance to each other. To do that, notice, okay, so here's the pair that I'm going to look at. S sub 2 to the n plus 2 to the n, in other words, 2 to the n plus 1, minus s sub 2 to the n. All right, so if this is beyond capital N, so is this one because it's even larger. So for this proposed threshold, here are two partial sums in the sequence of partial sums whose indices are beyond that threshold. If I can show that they have a distance to each other greater than epsilon, we're done. The sequence of partial sums is not Cauchy. All right, so what does this difference look like? Let me translate these partial sums into sigma notation. The first one goes from k equals 1 up to 2 to the n plus 2 to the n. Again, if you want, that's 2 to the n plus 1. And then we add up the terms of the form 1 over k. We are going to subtract off of that the finite sum starting at k equals 1 and going up to 2 to the n, 1 over k. Okay. This sum has all of these terms and more. So if we imagine expanding this and expanding that, both of them are finite sums. All of the terms in here are going to cancel out the first 2 to the n terms here. What are we left with? Well, we cancel out through k equals 2 to the n. So the first expression here that is not canceled out is 1 over 2 to the n plus 1. If I'm going a little too quickly, just imagine writing this out, and then cancel everything here with here. The first term that does not cancel is 1 over 2 to the n plus 1, and then 1 over 2 to the n plus 2. I'll just write another one, 2 to the n plus 3, all the way through this final term, which is 2 to the n plus 2 to the n. If you're curious why I kept writing 2 to the n plus 2 to the n, when that is really just 2 to the n plus 1, it's because I wanted to see exactly how many fractions I was writing here. So we can count them off literally. 1, 2, 3, 4, 5, 6. We have 2 to the n fractions here. If I make denominators larger, I make all of these positive fractions here smaller, I make the sum smaller. So what I'm going to do is take 1, 2, 3, all of these additions here, and replace them with this larger expression 2 to the n. By doing that, I shrink all of these fractions. I'm just going to write greater than or equal to. I don't need to be overly restrictive. So take this and go down in size by replacing 1 with the larger number 2 to the n. Same thing here. The only expression that does not get changed is this one. All right, so all of these fractions, their denominators got larger, the fractions got smaller, so we have a smaller sum here. That's why we have greater than or equal to. And because of the way I listed these off, we know exactly how many fractions we have here. We have 2 to the n. We can literally count them. And now they're all the same. And this time I'll write the nice form. It's not really necessary, but we could write 2 to the n plus 1, or you could write 2 times 2 to the n. The point is that when I multiply these two together now, I get 1/2. And just to keep writing to the right to save room, that is larger than epsilon. Okay, so for this choice of epsilon, I can go out really far as I like, just take n larger and larger in the infinite tail of the sequence of partial sums. And I can identify two partial sums very far out, whose pairwise distance to each other is greater than or equal to 1/2, which is greater than epsilon. Therefore, I'm just going to say the rest of this out loud. The sequence of partial sums for the harmonic series is not Cauchy, and therefore not convergent. And, that's the proof, taking this point of view of proving that the sequence of partial sums fails to be Cauchy. I like it. I like the cancellation here, or the kind of adjustment. I think it's very clean and works out very nicely. It's the same kind of maneuver that we do in the more traditional proof, where we show that just partial sums of this form. So when you take any expansion of the harmonic series, where you look at a partial sum that can be described as S sub 2 to the n, and then you kind of go down to 1/2. If you're looking at that proof, it's the same thought process as here. So we're taking things and shrinking them down so that we get this lower bound of 1/2. But I wanted to do something a little bit different. That wraps up this video. Thank you for your attention.